So hello everyone, I'm Dingyu from University of Michigan. Today I'm going to talk about optimal protocols for two-party contention resolution. So first, what is contention resolution? I mean, it is a very fundamental symmetry breaking problem where you have n devices and all of them need to acquire temporary and exclusive access to some shared resources without the assistance of a central authority. So in the abstract, it's basically you can imagine there are n players, and for each time slot t, where t is a natural number, each player can choose to send or remain idle. And if you look at a single time slot, if no player sends, we say it's a silence. And if exactly one player sends, we say it's a success, which basically means that player successfully sends his message. And if at least two players sent at that time slot, then we say it's a collision. So we assume that a player just leaves the game once it sends its packet successfully. And the question is, how should they do to just vaguely speaking, to send their packets sooner? So specifically, we assume that in our paper, time is partitioned into discrete slots, and all devices agree on slot 0. And the feedback is acknowledgement-based, which means at the beginning of each time slot, each device can choose to either transmit or not. If it chooses to keep idle, then it receives no feedback. You have no feedback unless you decide to send. And if you choose to send, then you will receive a feedback to indicating whether that transmission is successful or not. And we assume lossless operation. So the system is errorless. There is no environmental noise. And then we'll also assume anonymity, which basically is saying devices are indistinguishable and run the same algorithm, but they can generate their own random bits. So basically, if there's a no random bits, all of them will do the same, see the same, and the symmetry will never be broken. But given some fresh random bits, private random bits for each individual player, the problem is how to design protocols using those fresh random bits to break the symmetry as soon as possible. So in general, this problem is hard to come up with a precise protocol that is optimal. But if we only think about the simplistic case, where you only have two players, we want to know what's the precise, can we find precisely the optimal protocol in this simple case? But before that, if we want to talk about optimality in a precise sense, you really need to define the objective function precisely first. So let x1 and x2 be the waiting time for player 1 and 2. Both are random variables. And the randomness comes from the private random bits they have generated. And there are three reasonable objectives. First is the expected first success time. That is the expectation of mean of x1 and x2. And second is the expected average success time. Because x1 and x2 are symmetric. The average is just the average success time is the average waiting time of the first player or the second player. And they're equal. And the third reasonable objective is the expected last success time. So how long it lasts before the last player leaves. In other words, like the make span. So to solve this precisely, there is an important observation for the case where n equals 2. N is just the number of players in the channel. Is whenever one device receives a collision feedback, it knows that its history must be the same with the other device's history. Think about it. So initially they are the same because they agree on time slot 0 and nothing happens before. You can assume that. And then if one send and receive a collision feedback, that means the other one must have also sent at that time slot. And before that, if one send his message and the other keep idle, then that transmission must be successful, which is a contradiction because by assumption, once the player has succeeded, he must leave the channel. So if n equals 2, then we have this special recurrent property where if you see a collision, then essentially you are back to the initial state because the symmetry is not broken. Like you are as symmetric as in the initial state. That's why you can exploit this property to show that there must exist an optimal protocol that is recurrent, which basically says there is one optimal protocol that always restarts when a collision happens. It takes a little bit of effort to show this, but I guess it's intuitive enough. And now, if like among the class of all recurrent protocol, with a little more effort, you can solve out the exact optimal solutions for each of the 3 objectives. I wouldn't say the process of finding the solution is too interesting, but the solution itself are interesting. Let's first see the protocol that has the least expected average success time for two party is a simple 3-state algorithm. In the first state, it transmits with probability 4 minus square root of 6 over 3, which is about a little bit over 1/2. And if successful, then you just leave. If there's a collision, go to step 2. Step 2, it sends with probability 1 plus square root of 6 over 5, which is about 0.69. If successful, he just leaves. If not, he just goes to state 3. With step 3, he transmits with probability 1, which means he will, in some sense, will definitely, almost definitely transmit. In which sense, if successful, then he leaves. If otherwise, go back to state 1. Why? Think about it. Why this is a recurrent? Because, think about what will happen if 2 players are using this protocol. So if they are both in step 3, then there must be a collision happening, which resets the system state to the initial state. This is a surprising result because before this, we usually think of a resolution protocol as an infinite. For example, like the exponential backoff. One sends with probability 1/2. If it's a collision, it sends with probability 1/4. If it's again a collision, then it sends with probability 1/8. The sending probability just keeps backing off upon collisions. But for this finite case, for n equals 2, we have shown that if you want to minimize the average success time, the best thing to do is to send with probability 1 upon your like quickly. You can also do this for the expected first success, where the protocol is as we intuitively will think of, sent with probability 1/2 until successful. Why this is intuitive? Because if you have 2 players, to maximize the probability of a success of that time slot is to send with 1/2 probability. But if you minimize the first success time and you are one of the players, you don't need to, because you know if the other guy is present, has not succeeded yet, then you know he is the same as yourself. You see the same, you saw the same, you did the same. That's why you can always assume you are in the first place, like in the initial state. Because if you are not in your initial state, the other guy must have gone. And you don't need to care about those words because you are only minimize the first success time. And for the to minimize the last success time, it takes a little bit more effort, but it's not that hard once you realize that there exists a recurrent version of it. It can also be described in 3 states as this. So to understand this, maybe insightful to understand the general or when like n is large, because even when you are considering a general n devices, you are trying to resolve a general collision of size n. The usual method to do it is also try to back off with the correct probability and get a population with constant expected size. So to understand like continuous resolution of size 2 may be helpful in that case. But in reality, there is some case where like in the processors, maybe there are only 4 processors or 2 processors where there is a scenario such that this is needed. Okay, so then naturally, one will ask, can we generalize this method to n equals 3 or even n equals 4 or n equals 5? Turns out that it's a quite very challenging problem. Personally, I've been thinking on extending to I've been working on understanding the case where n equals 3 for quite some time. But it turns out it's very challenging because you lose the recurrent guarantee your like optimal solution. Yeah, as it, yeah. But also an interesting question is, recall that for, let's say, for all the objectives we have come up before, it only takes a finite state protocol to be optimal. So before really finding like the optimal solution for n equals 3 case, is there a finite state protocol that minimizes the first success time when n equals 3? This makes a lot of difference, because if the answer to this is true, then basically you can enumerate by the number of states of all possible protocols. So like there is a way to enumerate all such protocols, and you are guaranteed to find such eventually. But in all, this becomes really challenging once n goes to 3 and above. Also, to minimize the first success time, expected first success time when equals to 3, sending with probability 1/3 is not optimal. So even this like simple case is not trivial at all. So yeah, that's just wide open. Yeah, that's it. Thank you for listening.